Yeah, good morning and welcome to this session on choice experiments. Before we start, may I just ask you to remember to please switch off your mobile phones if you haven't done so. The first speaker in our session is Martina Vandebroek from the University of Leuven, and she will be speaking about conjoint choice experiments for estimating efficiently willingness to pay.
Okay, good morning. I'm presenting joint work with Peter Goos, who most of you know, Ricardo Scarpa, who is at the University of Waikato, that's in New Zealand, and then Bart Vermeulen, who is a PhD student and who did, in fact, all the work, all the hard work. I was not sure that you're all familiar with conjoint choice experiments, so I will start with a brief introduction to conjoint experiments, or also called stated preference experiments. So the idea is that you want to know what makes a product attractive in the eyes of the consumers, or why people prefer brand A over brand B, or what people are willing to pay for some extra feature of a product. Then you can just show them some products and ask them for their preferences, okay? So you ask people to state their preference, and that's why it's called stated preference experiments, because it's different from revealed preferences where you just look what they buy in the shops. So this is not really buying products, but just stating preferences. So that's why it's called stated preference experiments instead of revealed preferences. So here's an example. Suppose you want to know whether they prefer a larger hard disk or perhaps larger internal memory, or what they want to pay for a larger screen, for instance. You can, for instance, provide them with these for different laptops. And what's typical here is that a product is described as a combination of its features. So it's really just a combination of features, okay? And so it has been shown that you get more reliable results if you consider all these attributes at the same time instead of one by one. Not just asking what do you want to pay more for a larger screen, or would you like rather a larger hard disk than a larger internal memory. It's better to give full profiles and let them state their preference for all these different profiles. So you consider all the attributes jointly, and that's why it's called conjoint analysis, okay? Now there are a lot of different conjoint experiments. I give just the main ideas. You have rating-based conjoint experiments where you just ask the people to rate different profiles. For instance, the top laptop would have a rating of 100 and a really lousy laptop would have a rating of 0, but then you have all those ratings in between. That's rating-based conjoint experiment. Or you might use contingent valuation experiments, where you just ask the people what they would pay for each laptop. Or that's open-ended. You can also give bounds. For instance, would you give 1,000 euros for the first laptop? Would you give 500 euros for the other laptop? So you have a lot of different ways to state the preferences. Or you may ask the respondents to rank them. Which do you prefer, which is second, and so on. Or you might put all these profiles in smaller subsets and ask the respondents to choose the most preferred one in each choice set. That's called discrete choice experiments, and we will deal mainly with these discrete choice experiments. It should give the most reliable results because this mimics best to what they are used to. The respondents are used to choose in the shop between different laptops, so as this mimics what happens in reality, this should give the most reliable results. So here I have put the 4 profiles in 2 choice sets, and so you would be asked to choose which one you prefer here, so a large hard disk or a larger internal memory, for instance. And here there's also difference in weight, so you have to choose the most preferred one. And so the design problem will be obvious, I think. So you have to choose the profiles that you will show, what combinations of attributes you will show. And for the discrete choice experiment, you also have to decide how to put them in smaller sets. And this is not an easy problem, of course. For this very small laptop example, you can find almost 500 different choice sets of size 2. And you can't ask people to rate 500 choice sets, so you have to make a good choice. Okay, the design problem, of course, depends on the model that you use to analyze the results. Now, for the rating-based and contingent valuation experiments, linear models are typically used, which simplifies the design problem. For the discrete choice and the ranking experiments, people often use a conditional logic model or combinations of this model, which is a nonlinear model, which poses extra problems. Okay. I will have to explain the model a little bit because I refer to this later on. So the conditional logic model has been derived by first giving an expression for the utility. So this is the utility that the person M obtains from profile J in choice set K. Looks complicated. So I have different choice sets. The choice set is denoted by K. What is the utility that he gets from alternative J? It's a linear combination of the attribute levels. So the x's describe different attributes, the size of the hard disk, internal memory, etc. And the betas give what I call the part words, the value that people attach to these attributes. Okay. And we are, of course, interested in these betas, because then we can make predictions for new products, for instance. Okay. So this is the same model. I wanted to point out that the x's do not have a subscript m for the respondents, so I assume that all the respondents get the same choice sets, same profiles to rate. And also, what's perhaps less obvious is that the betas have no subscript m, so I assume that they all have the same part words. They all attach the same weight to a certain attribute. Does it seem very logical or realistic? But it has been used very often like this. I will say some words about the extension later on to heterogeneous populations. Okay, so if you start with this expression for utility, and then if you assume that the epsilon has Gumbel distribution, it's possible to derive this expression. That's the probability that alternative J is chosen in choice set K. So it depends on the alternatives, on the attributes of the Jth alternative, and on all the other profiles in the choice set, of course. Okay, if we want to estimate the betas, we use maximum likelihood. That's a regular log likelihood expression. And you can compute the information matrix, and so also the variance covariance matrix of the betas. So it has the design matrix. This describes the profiles in choice set K. And this matrix, diagonal matrix, and these vectors contain all these probabilities that alternative 1 is chosen in choice set K, alternative 2 is chosen in choice set K, until the last one. Okay. Okay, so what have we and others been doing? Looking for the optimal designs, minimizing the variance covariance matrix around the beta. And of course, it depends on the beta through these these probabilities. So you can look at locally optimal designs. That's what a lot of people have been doing. Putting beta equal to 0. And then the problem simplifies considerably, because then the design problem is equivalent to the design problem for a linear model. So that's convenient. But in fact, it's not hard to see that beta equals 0 is not very realistic in these applications. You know that people would prefer a larger hard disk and a larger internal memory. So for most of the smaller price, so for most of these attributes, you know the direction or the sign of the coefficient, you just don't know the size. So it has been shown that if you include this information in the beta, you get better results. Now what we have been doing mainly is looking at semi-Bayesian or pseudo or quasi, I don't know how to call them, Bayesian optimal designs where we take a prior, so we include all possible or realistic values of beta, and we take the expected value of the variance-covariance matrix, the determinant of the variance-covariance matrix. Okay. That's what we have been doing, and others have been doing. Now I come to the marginal rate of substitution and the willingness to pay. So more and more these models are also used to compute marginal rates of substitution. And what do I mean with this? You try to find out how much this attribute has to go up when another attribute goes down so that the utility remains constant. Okay? It's not difficult to see that this is just a ratio of two of these parameters. And when one of these attributes is the price, so if one of the two attributes is price, it means how much are you willing to pay for an extra feature, then it's called willingness to pay. So this is just a special case of the marginal rate of substitution. So we are interested in these ratios. They have been used a lot lately in marketing transportation, where they were using discrete choice experiments already for a long time. In the other areas, like environmental economics, healthcare, they have been looking for willingness to pay estimates for a long time, but they used mainly contingent valuation. They would ask people, are you willing to pay this much for less air pollution or to preserve national forest, rainforest, and so on. But now they found out that using discrete choice experiments gives more reliable results. So more and more these discrete choice experiments are used to estimate willingness to pay. And it has been used already a lot. What designs do they use? Very often just random combinations of attributes, or fractional factorial designs or orthogonal designs. So they decide based on this what combinations of attributes to include, and then they put them randomly in choice sets very often. Okay. So we have already derived, and others have derived, locally optimal designs and semi-Bayesian optimal designs that are most appropriate for estimating the betas. But it has been shown, and I will show you later on, it often gives rise to unrealistically large willingness to pay estimates. So we look for designs that are more efficient for estimating willingness to pay. So we started with this approach. We need an expression for the variance of this estimate. We used the delta method, so we have this approximate variance for this ratio. And then we looked, we have not just one attribute, one willingness to pay, but n-1 willingness to pay terms. So we want to minimize the sum of all these variances of the willingness to pay estimates. Okay. Of course, this depends on the beta again, and we will take a semi-Bayesian approach, putting a prior on the possible beta values and then minimizing this integral. Now, this is not obvious. You have to approximate it and do some clever tricks to get this computed in realistic times, but I will not go into detail here. I guess the next speaker will say more about numerical problems, computational problems. Just want to illustrate whether this works. With a small experiment, you have two 3-level attributes, one 2-level attribute. They are effects type coded, and I have 2 price levels, 12 choice sets, and 3 profiles, and some respondents. So I take the semi-Bayesian approach, so I have to specify the prior. And what you see here is, well, these two belong to the first attribute. It has 3 levels, effects coded. And this just means that the lower level has lowest utility, middle level, middle utility, largest level, largest utility. That's what you have here. This is the same for the second attribute. This is for the third one, which had only 2 levels. And so this is also, the larger the value, the higher the utility. And this is for the price. The idea is that the higher the price, the lower utility. So it's quite intuitive, I think. This is a variance-covariance matrix. Making sure that the price coefficient is always negative, whereas the others may become positive. Okay, I compare my willingness to pay optimal design with some other designs. For instance, just the optimal design for beta. And then 3 other designs that we generated with the Sawtooth software. I don't know whether you know this. It's used very often in the marketing world. You have several options there. For instance, computing a near orthogonal design, where they make sure that every attribute level appears an equal or almost equal number of times, but not the same level attribute in the same choice set, and it's close to an orthogonality. Or they just have random designs, making sure that it's not singular, the information matrix, but otherwise it's just random. Or allowing for some overlap, so that you have the same screen size, for instance, in one choice set. Now, if you look at this WTP error, Bayesian error, of course the WTP is optimal because I constructed it this way. But you see that the D-optimal is not so different, and the other 3 do much worse. Now, to get a feeling for what this really means, we did a simulation study where we drew a beta value, generated responses, estimated the parameters, computed the implied willingness to pay, just this ratio. Do this for different data sets and for different betas. And then, yeah, these are the real numbers. And we looked at the mean squared error. So how different are the estimated willingness to pay coefficients from the real willingness to pay coefficients for each beta that we have drawn. What you see here are partial results. These are log values because some values got really very, very large. So the largest ones have been topped off. The largest ones are those larger than 6 times the interquartile range. As it's not complete, I prefer to look at this table. So here you have the 5 different designs. The willingness to pay optimal one, derived by our new criterion. The D-optimal, looking for the best designs for estimating the betas. And then the 3 sawtooth designs. On average, this is, over the different betas, this one is best, closely followed by the D-optimal design. And then this gets worse. Well, this doesn't look that bad, but if you look at the maximum values, for some betas, it really goes way off. This is typically what has been mentioned in the literature. You often get really unrealistic high willingness to pay values. And it seems that we have reduced this at least somewhat by our new designs. The D-optimals are less extreme than the others here, than these 2, but still much worse than the WTP optimal designs. Then we also looked at the efficiency for estimating the betas, but I will skip this. Also looked whether, oh yes, I forgot to say that in the previous picture we have drawn beta values from the prior distribution, so it's perhaps somewhat cheating. We assume that we had the right information for the prior. If we draw beta values from another distribution, things do not really change. So that's good. So I will skip this, also the beta values. So we did already a lot better for estimating the willingness to pay than the more standard designs, even better than the d-optimal designs, but we still had some outlying values. So we tried to find other criteria to get rid of all the outlying values. Now I call the criterion I had before the C-optimal criterion, because they will all be somehow willingness to pay optimal, all the criteria that I have now, because they are all meant to do the same thing. So this is what I had before, as approximating the variance of the willingness to pay by the delta method, and then minimizing of all the sum of all these variances. I compare it as before with the d-optimal design, standard d-optimal design, also the a-optimal design. But then as I want to top off these large variances, I have a new criterion minimizing the maximum variance, hoping to get rid of these extreme values. Also minimizing the variance of all these variances, hoping to get rid of these large variances. And so in all these cases, the variances are approximated by the delta method. Then there are a few very different approaches. I don't know whether you are familiar with the Wheeler theorem. It gives a method for computing confidence intervals for a ratio of linear combinations of betas. So it looks quite complicated, but here too you have something that measures the precision. So if you minimize this thing, you should also get more reliable estimates. So it looks complicated formula, but it's not important. It's just that we minimize this width of this interval for all the attributes that we're interested in, and then over the prior distribution. Another approach is what's called M-optimality. So if you would have several linear combinations of the betas that you're interested in, and you put the coefficients in an M matrix, then this would be the variance-covariance matrix of the different linear combinations. So we can use the same approach, but instead of having the coefficients of the linear functions, we take the derivatives of the functions with respect to beta. So it's an approximate method. And then this should be an approximate variance-covariance matrix of the different willingness to pay coefficients. So there we can use a d-optimal approach, but then it's called M-optimal to distinguish it from the real d-optimal design. And then I have three very different criteria for which I have to change my utility function. It's not invented by us. The people who had problems estimating the willingness to pay have used this approach too. So what you see here is the same expression as before for the utility, but now it's multiplied. Every term is multiplied and divided by the price coefficient. So, and then this here is the willingness to pay. Well, except for the sign, which has gone. But okay, so you have an expression for utility in terms of the price coefficient and the different willingness to pay coefficients directly. So you can directly estimate these coefficients instead of first estimating the beta 1, beta 2, etc., and then taking ratios. You can use maximum likelihood estimates of these willingness to pay coefficients. Then you can derive the information matrix. So this is the information matrix with respect to the willingness to pay coefficients. This with respect to the price, and then covariances. So then you can again look at the optimal approach, or a optimal approch, or a var-min approach where you minimize the variance of the variances, and so on. So I have a lot of criteria here. They are summarized. So I have designs that look for precise estimation of the betas themselves. Here you have the three criteria that look at the willingness to pay coefficients, the variance of the willingness to pay coefficients, which is approximated by the delta method. You have this feeler method, you have the M-optimal criterion, and then you have criteria based on the willingness to pay estimates themselves and the willingness to pay space. Okay. I show you the results of a simulation study. It has 8 choice sets, 3 alternatives. Well, it's not that important because we did several simulation studies and the results are more or less the same over different applications. Here you have all the values in this plot. It's again log, so don't know, log of almost 20, that's a huge number. Logs of exponent of almost 20 is huge, exponent of 10 is also huge. So it doesn't look that bad because it's on the log scale, but all these values are really very far off. Okay. It seems that these 3, minimizing the maximal variance or minimizing the variance of the variances of the feeler approach, and perhaps here the A-optimal approach and the willingness to pay space, can avoid outlying values. Well, this is how good they perform for estimating the betas. It looks also rather bad, but the scale is very different. They're all not too bad. The scale is only until 2. This is for, the previous was for the correct prior, here for the incorrect prior, but the results are mainly more or less the same. So we have 4 criteria that perform best, I think. That's minimizing the maximum variance, minimizing the variance of the variances, this feeler approach, and then the A-optimal approach in the willingness to pay space. Okay. This is for the betas again. Well, I don't have much time, perhaps 1 minute. Just 1 minute to say that we are working now on the heterogeneous population. So until now, I assumed that the beta was the same for every person. So every person attached the same weight to the larger screen or the larger hard disk. More and more people are using mixed logit models where the beta is assumed to have a distribution. So this is the mean value in the population and there is some variation. We have been working on computing designs for estimating the mu and the sigma then efficiently. This will appear later this year in marketing science. So these designs were for estimating the mu and the sigma most efficiently. Now we are working on estimating the distribution of the willingness to pay in the market as efficiently as possible. Stop. So, yes. And we are also working on the semi-Bayesian approach to see whether other criteria, taking into account the prior distribution, might do better. But then I will stop here, not giving results. Thank you.
Time for 1 or 2 questions. Yes, Henry?
You're looking at these substitutions, these ratios, but if I don't know what your number of parameters is, so I forgot K. So it's K choose 2 ratios. So if you only look at K minus 1 ratios, you're losing some symmetry. Did I miss something? Because you can have all possible beta i's upon beta j's. That should be K choose 2 ratios. So somehow you need to preserve the symmetry in your optimization criteria.
People are only interested in these willingness to pay ratios.
But there's a lot of them. Each
divided by the last one.
Yes, so there's K choose 2 ratios.
No, then you need to take all.
No, but if you decide what a denominator is, then you're losing symmetry.
Yeah, yes.
You have B1 upon B2, B2 upon B1, B1 upon B3, B2, B. Okay, so it's always worried me that with these things that they always fix on it one way up unless it's invariant. Unless the criteria is invariant under factor, then you're losing symmetry.
And what's the problem with that?
The last variable is price.
Yeah.
Yeah, I don't see the problem with losing symmetry.
Very,
symmetry because it's price.
perhaps very quickly, Rainer.
I would have two concerns, but let's say just one concerning the outliers. So, and I have some concern about the outliers are really outliers because you are looking at ratios, and if the numerator and the denominator are normally distributed, you get something like a non-central t distribution or Cauchy distribution or whatever, and there should be outliers in there. So I'm not quite sure whether you can catch anything by the expected mean square errors in there.
Well, we know the real willingness to pay coefficients, and we see how far we are off. Of course,
but
perhaps-
the average does not converge at all.
okay,
have to
but
look for
what do you
quantiles.
suggest then for practical purposes?
You have to look for quantiles, not for what in a way you did. So the outliers have to be there. You cannot get rid of them.
Not completely, but try to reduce them seems possible.
Yes, it
Yeah.
means you have to reduce somehow the tails.
I think I think we have to move on. So thank Martina again.